Hello everyone, welcome to the lecture on machine learning. I'm Volker Tresp, I'm a professor here at the LMU and I am also with Siemens Research, where I have the title of a distinguished research scientist. So these are new times, difficult times, so we're trying to do the lecture by recording it. And we have to see how this works. So I will give a little bit long overview about different topics, background topics, which are relevant to machine learning. And it's pretty non-technical. It has gives you some understanding of the background of the field, where it's coming from, how it is maybe also evolving, why it is how it is. So this is more to give you an understanding than relevant for any exam. So I will start with an introduction, then talk about non-technical perspectives on learning, then discuss machine learning, so the technical aspect, and then some details on the lecture. So why is machine learning of interest? The thesis is learning is one of the three fundamental mechanisms for the design and the improvement of autonomous intelligent systems. So what are these three? So the earliest and the first one was evolution. It's essentially improvement by trial and error. It's a biological mechanism. Richard Dawkins called it the blind watchmaker, in the sense that it produces something as complex as humans, but it sort of acts blindly by trial and error and exposure to the environment. Technical evolution has something in common with this aspect, because the know-how in the company and state of the art is really also a lot to do with evolution of an environment you're joining, where there's a certain know-how with looking what the competition is doing. So there's some form of crossover. So it's not just that you come from the university, you know everything. You're a part of a existing business environment, typically, or a technological environment, and you can learn of it, and it sort of evolves in an evolutionary manner. It is simple, blind by mutations, by random changes, and it's self-optimizing. So these are two big advantages. There are also disadvantages. Of course, it's slow. So the time constant is years, decades, maybe century. And it's wasteful. No? So you have to try out a lot of things before you find something which improves your solution. Then maybe the second one is learning. There's a biological aspect, which essentially is a lifelong optimization of the behavior of an individual via interaction with the environment. So in a way, it's the learning watchmaker. Maybe there's a teacher, then it's an apprentice watchmaker. So that learns from a teacher and personal experience. And it's a basic property of animals. It's almost seems to be a natural law, because quite primitive animals are able to improve their behavior by learning. Feedback comes from the learning success, sometimes called reinforcement, and it's quite fast, maybe on the order of days. Machine learning, in the broadest sense, is the attempt to mimic biological and human learning for technical purposes. And the autonomous optimization of a technical system via interaction with the environment, so that's more the agent or robotics view, or by analyzing acquired data. So there's this nice expression, learning instead of programming. In this lecture, we will mostly deal with the second aspect, that we have data and we want to learn from this data. So what is number 3? It's intelligent design in the sense of what we are doing when we are engineers or programmers, because almost all technical solutions are based on intelligent design. If you look at your car or your smartphone, there probably starts to be more and more of machine learning in it, but basically it's a human engineering output. So you can call an engineer the knowledgeable watchmaker, which we don't mean the divine watchmaker by so some sort of godlike future. I mean the human knowledgeable watchmaker, so programmer, for example. There are many advantages. The knowledge is explicit. The system is well understood and can be analyzed, can be debugged. Can be improved via analytical thinking. The time constants here are maybe years before you become an experienced watchmaker. The disadvantage is you need a human, somebody who's able to understand complex issues. Maybe you need a teacher. So I said definitely need an expensive designer. So what is technical progress? It's sort of advancement of the state of engineering by informed trial and error. So that's step 1. By a set of knowledgeable learning actors driven by customer needs, competition, and business opportunities. And occasionally, so it's sort of an evolutionary process with some smartness. And occasionally there are paradigm changes, so a new technology comes across. And it might infect the way you work, the way your products are designed, your environment. So, for example, search engine, or this whole way that the web, Wikipedia, and others provide us with knowledge definitely changed across different areas of business and activities. So, what is learning? So learning is an exclusive properties of living beings, and maybe nowadays computers, and even quite primitive animals can learn. As I said, we will talk about Aplysia, which is a sea snail, a pretty simple animal, but it already has been proven that it has learning capabilities. So biological learning is about modifications in the nervous system. It should be beneficial. So if you just damage your nervous system, you wouldn't call it learning. It should be permanent. So if you immediately forget about it, you probably wouldn't call it learning. It's a lot in the central nervous system, in humans at least. And it's based on experience, on interactions with the environment. So there is the better brain hypothesis in the sense that my brain today is better than my brain yesterday, and even now I'm trying to make your brain a better brain. I'm changing your brain, which is sort of scary in a way. Machine learning, we want beneficial changes in a technical system based on the analysis of data or based on the interaction with the environment by employing learning algorithms. So where does the word come from? From English lernen, or Proto-Germanic lisnoyan. And these words have a lot to do with tracks with finding tracks, but also leaving tracks, which is quite fitting because learning has something to do with leaving traces in the brain. So this was the introduction. Now we come to the non-technical perspectives on learning and AI. So we start with philosophy, then psychology, cognition and cognitive neuroscience. So philosophy is more about what can humans or humankind know, what can we learn, how do we know what's going on in the world. Psychology, cognition, cognitive neuroscience is more how does an agent, an individual learn when the individual grows up and matures. And cellular neuroscience is sort of the level of where things are really happening on a physical and physiological level, and all of them have something to do with learning. So in philosophy, it's related to epistemology or Erkenntnistheorie, so the theory of knowledge and justified belief, and it's really about what mankind really knows and how mankind acquires knowledge. So how can we know anything, and how can we study how the world functions, and what is knowledge? And quite recently this was still answered by religion, so that we have a science here, and a philosophy is only a couple hundred years old. And there are two important mechanisms, and this will show up all over today's lecture, but also in the future. And the two things are deduction and induction. Induction, you try to make inference from the general to the specific, top down. So, and what you have to start with something, and you start with so-called axioms. So they're given or they're assumed, and then theorems, so that's new knowledge, are derived via the machinery of deductive reasoning. And in axioms, we really have to make a distinction because they consist of simple facts. So Jack has blue eyes, and we call them data, measurements, maybe knowledge graphs. And they're complex axioms. So if something is a dog, it's also a mammal. So if I know that something is a dog, I can make the inference and derive the theorem that this thing is also a mammal. It was founded or started with Aristotle, so before Christ. And one interesting thing is that it has a relationship to language theory. So do we speak in axioms? Do we, when we convey facts at least, it's very close to facts which are true in the world. Maybe sometimes we even communicate complex axioms. So that has also historically been explored a lot. And it's also the basis for the classical artificial intelligence from 1954 to maybe 1985. The second principle is induction, where you try to generalize from observations. So you first observe, and then you discover regularities, and then you might conclude that something is true. It's typically considered a bottom-up procedure. And the goal is to generalize from the observation and to justify theories. You cannot prove theories. Or inferring the validity of a hypothesis via observations and experience. So simple facts are sort of the same as in deduction. So Jack's height is 180 centimeters, so Jack has blue eyes as in deduction. But the complex axioms and the logical reasoning is replaced by learning, often with a statistical nature. So dependencies instead of assumed complex axioms. So this is typically closer to reality and quite powerful because For example, we can deal very well with exceptions, so we make probabilistic statements. But the disadvantage is that this type of learning, the outcome might be difficult to explain. Whereas on the left side, on the deductive side, these the complex axioms often have the flavor of a rule, which can be communicated by language, as I said before. And induction is the technical basis for machine learning and modern AI. That's why the lecture is called machine learning. And this plays in different in the history of philosophy. So now we're becoming a little bit philosophical. So it started off with rationalism in the 17th century. From Latin ratio or reason, and the hypothesis, let's mostly trust our reasoning capabilities. So we have this complex axioms. We know how to do inference. There's a priority of rational reasoning in knowledge acquisition. So that's already a big step ahead before we had religious convention. And often associated with Socrates before Christ and Plato. And then in modern times, René Descartes, Spinoza, and Leibniz. So it's sort of associated with the introduction of mathematical methods into philosophy. And it's also typically associated with a continent, so with continental Europe, so excluding the UK. Because in Britain has a slightly different tradition here, which we come next. So proponents of some varieties of rationalism argue that starting with foundational basic principles like axioms of geometry, one could deductively derive the rest of all possible knowledge. Now that sounds like deduction, like the left side of the slide before. So yeah, as I said, in the UK and in England, Britain, there's a slightly different tradition. It's based, so empiricism was much stronger there. So so where does the knowledge come from? So let's not speculate as much and come up with axioms and theorems, derive theorems. Let's mostly trust our observations, so facts, data, measurements. So it's a bottom-up approach. Comes from the ancient Greek word empiria, which translates to the Latin experientia. It's a British tradition. And John Locke, for example, said there's nothing in the mind that was not first in the senses. So he trusts more the senses than the mind in a way. And so the mind started as a blank slate or a tabula rasa. So you start with nothing and everything is through the senses. Here representative mentioned already Aristotle, Francis Bacon, John Locke, and David Hume. And then so Aristotle and Locke, and they started a very simple way of associations. So that was going beyond simple facts. So it's a little bit also going in this personal direction of learning, not just about learning about the world. But for example, if two things happen together, there's some association between the two things. If things are repetitive, if there are certain associations like pleasure and pain, and so on. So that's sort of the way Aristotle started thinking in this direction. And the laws that taught association and so on, in some sense, they're still the backbone of modern learning theory. So thinking about these things is quite the basis. It's a little bit also about how humans act and acquire knowledge. And one interesting thing, so the distinction between rationalism and empiricism is a little bit like the distinction between probability and statistics, which we will learn about. So probability is a mathematical theory based on theorems, based on axioms and derived theorems, and statistics is much more based on looking at things, statistics in the world, and deriving knowledge from observations. And of course, that also, to some degree, explains why machine learning statistics has a much stronger tradition even today in the Anglo-Saxon countries and culture circle. Next came idealism. So a little bit as a conclusion, a synthesis of the two. So there, it's not about reasoning or experience; it's about ideas, and that's probably is more so in the view of a social context of the way society works. You know. Mind over matter. Let's trust mostly our mental self, and people are driven by ideas and visions. So reality, as we know it, is fundamentally mental, mentally constructed, or otherwise immaterial. So ideas, especially beliefs and values, shape society. So there's a tradition from Plato. Reality is just a reflection of non-physical ideas, and the material world is an illusion, which also has a tradition in Hinduism and Buddhism. And a skepticism about the possibility of knowing any mind-independent thing. So Berkeley, Kant are typically considered here. And even today we talk about idealism or idealists, about people who are driven by ideas. And also there's a long tradition in Germany, Hegel, Fichte, Schelling, Schopenhauer. They dominated 19th century philosophy. So that was nice, but then the success of science started to come about, and people had a more were impressed, I guess, by the success of science, and the underlying philosophy is called positivism. So knowledge is derived from positive findings, and positive not in the sense of not negative, in the sense of certain. So certain findings. That's why it's called positivism. So it's in a way it's a let's mostly trust science. So the idea is that all true knowledge is scientific, and all things are ultimately measurable. Galileo was sort of the founding father here. And data and mathematics together are the source of all authentic knowledge. And this is probably true in a lot of scientific domains, in particular if you're talking about hard science like physics. But then they also applied it to sociology and the way people interact in societies. And here representatives are Auguste Comte and Macher and Durkheim. A proponent of, and of course this is sort of can be criticized, and that's also the start of the next wave. Steve Hawkins calls himself a positivist because he believes in models which can make predictions. So it's still, I mean, people who just died or they're still alive are positivists. So that's still very much around in science, of course. Eugene Wigner stated about the unreasonable effectiveness of mathematics in the natural sciences. And he's right. It's sort of surprising why mathematics tells us so much about nature, or as a tool to understand nature. And something related to this idea is materialism, but of course it's a different direction with Feuerbach and Marx. Even history is driven by ideas and by laws. although most would not consider them to be positivists. But I think this influence of science was so strong that even this principle of scientific discovery and evolution was applied to also questions in society and the way economy works. There are newer versions of positivisms. They're called neo-positivism or logical positivism. And the idea here is that maybe we can formalize all of knowledge in terms of mathematics and theorems. And that was quite a strong and influential philosophical direction, even in the 20th century. Gottlob Frege, Bertrand Russell, Whitehead, they tried to set up the Principia Mathematica. They sort of got a problem because of Gödel's incompleteness theorem. You cannot prove all true sentences in sufficiently complex domains. But it had a lot of influence on the start of AI in the 50s. So some of the extensions here are variants as the Wiener Kreis, which is quite influential, with Rudolf Carnap, who had then great influence in the US, or another person to be mentioned here is Ludwig Wittgenstein, who related it also to language issues. Yeah, but then when people, as I said, tried to apply it to sociology and society, it was not so clear that scientific methods and scientific thinking is really so applicable there. So the sort of the counter movement is sometimes called anti-positivism, or Max Weber, who was also in Munich, is a representative here. So they say it's not necessarily ahistorical what is happening. It's in the context of the social interaction with people. There might not be this really general laws. There might be more evolution of society. The rejection of science or scientism as a science of ideology, also expressed by the Frankfurter Schule, which was quite influential in the 60s, Herbert Marcuse, Adorno, Horkheimer, Fromm, Habermas. And another direction which also tried to make positivism more relative is post-positivism. So science is not independent of the scientist and the culture. We'll come to this later. So now, of course, researchers work in a social environment with leaders and egos and paradigm shifts. We will discuss this also in a second. So maybe this is even more to the point of current scientific thinking. And this was developed by Karl Popper, and it's called critical rationalism. And the main statement is that only falsifiable theories should be pursued. So he agrees that induction, so learning from data, is really the key, and making hypotheses on learning from data. But then the problem is induction is not sound, some people say, and it means essentially that if you just observe something very often, it doesn't mean that it's necessarily true. Example, will the sun rise tomorrow? It has always risen every day, but it cannot really prove that it will also rise tomorrow. And this is a little bit maybe depressing. If no finite set of observations can ever prove a theory, how can we ever accept a scientific theory as being true? And Popper accepts empiricism and accepts or states that theories can only be falsified. So if you find one counterexample to your theory, it's untrue. But if you never find a counterexample, it doesn't mean it's true. And this idea of falsifiability has a lot of influence in science, of course, if you make a statement about how your brain works and there's no way of testing it, then people wouldn't consider it to be a scientific theory. For example, Freud has this problem. We'll discuss also in a second. This sort of emphasizes the sociology of science, or the structure. And this person is called Thomas Kuhn. He's a historian of science, or was one. And he coined this term of a paradigm shift, which means that science doesn't evolve as linearly as maybe scientists like to convey. It's following some ideas or some paradigm, it's called, and then maybe somebody dies, or for some other reason the paradigm is switched, and people follow another way of looking at problems. And it's probably more true in the softer sciences than in the hard sciences, but still, I think every researcher would pretty much agree with this. Of course, we are all human beings. We are all living in a society. We have to get a paycheck. We have to have a career. So there's a social environment we're acting in. So everybody would agree with this more or less. But then some people even went further and sort of claim that there's nothing really special or true about science. It's just a social enterprise like many others. And there people would not agree. So Paul Feyerabend is considered a representative of this idea. There's no demarcation in terms of methods between science and any other form of investigation. And people don't accept that. I mean, there are some constants in physics which have been calculated with an incredible accuracy, and this was then confirmed by experiments, and this cannot just be a social construct. There must be something underlying which is true in some sense. Yeah, so Popper's falsification has great influence. And what is the basis for classical AI and machine learning? So it's definitely this idea of falsification. Then logical positivism, like Ludwig Wittgenstein and co-workers, definitely had a big influence on the development of AI in the 50s and 60s and a little bit later. Empiricism can be considered the philosophical basis for machine learning. But again, I mean, the distinction is not as big as you might think, because both logical people and machine learning people, or classical AI people and machine learning, would base whatever they're doing on simple facts. And the nice thing about simple facts is that people can agree about them. Maybe 99% of people would agree with the fact. Whereas people don't really agree on axioms, and the problem is also with axioms is there are often exceptions. Purely logical approaches don't really deal well with exceptions. So this philosophy is mostly, not exclusively, but mostly concerned about what can we know and how can we learn and how does society work and so on. Of course, we are the learning machines in a way. So each individual of us, every animal, has to interact with the world and learns continuously. Psychology is the study of the faculty of the mind, in particular of learning and behavior, and is focusing on the individual. So humans are mostly the system that produces data to be studied, happiness as a function of income, child development. And in psychology, you're emphasizing sort of this input-output study that you do questionnaires, you do sort of studies with students and so on, and you're trying to analyze the data. And cognition is more the view that you try to understand the working of the brain, maybe with mathematical methods and theories. And cognitive neuroscience I found interesting. It's connecting psychology and cognition, also with neuroscience. So it's trying to look at the whole picture. Psychology as an empirical science really started with Helmholtz and Wundt. So they studied typically, let's say, how the eye works, how the ear works, what are the limitations of the eyes, what are the limitations of hearing. So it's a lot about perception or Sinneswahrnehmung. But it was sort of the first group of people who looked at humans in this context as an object of scientific study. Yeah, it's about the study of the relation between stimulus and sensation, for example. And for example, Hermann Ebbinghaus was the first one to start to study how memory works. How long do we maintain memory? Under which conditions? Is there a preference for certain memories? So suddenly the human being became center of psychological study. Then you probably all heard about Sigmund Freud. He started something called psychoanalysis. And he was sort of the opposite to psychology. He did essentially science by introspection and by interviewing people. The hypothesis is people can be cured, so it's also about people who have a mental disease, by making conscious their unconscious thoughts and motivations, thus gaining insight. Some critics regard it as pseudoscience, so not a real science, because you cannot falsify a lot of the results. But of course, psychoanalysis had a lot of influence on psychiatry, which is a branch of medicine. So that was an interesting progress or direction of progress, and then maybe also a bit as a counter reaction to psychoanalysis, behaviorism came about. Central statement is belief in the existence of consciousness goes back to the ancient days of superstition and magic. And it rejected the idea or the theories which had to assume mental states. So no interest in explaining what is observed. The inner structure in this way, in this interpretation. So the inner structure of the brain is irrelevant, and functioning of humans can only be deduced from input, stimulus, and output reaction. And humans are just another animal to be studied. There's nothing special about humans. And humans start tabula rasa, so everything is acquired from the external world, and we don't really have to understand what's going inside. And this is it's also very positive. First of all, it's still going on. It's still what people are doing in psychology, and the insights are sometimes really interesting. And it's in a time, this was developed in a time when racism and fascism was popular, so making some of these statements was quite revolutionary at the time. And famous names are Pavlov, John Watson, and Skinner. So here's, just to give you a feel for this field, classical conditioning from Pavlov, learning to predict important events. So it's about the dog. And there's different phases. In phase 1, we are checking what is called unconditional response. So the dog is exposed to the unconditional stimulus, let's say smell of food, and produces the response, salvation. Now, since the dog has learned early on that food smells good, and after food smell comes food. Then in the second phase, the dog still gets the food, but before, or is exposed to food smell, but before the dog also hears a bell. So, and the bell is called conditional stimulus in this tradition. And then, of course, after a while, the dog knows that when the bell rings, I will get food. So salvation starts just based on the bell, even without any food smell. So the bell is called conditional stimulus, and the food smell is unconditional stimulus. And as a predictive model, this makes, of course, absolute sense, because there's a hidden cause, HC, which is the experimenter, which does both. So why wait for the food smell if the bell already tells me about the reward? And this is also a deep problem in machine learning, of course, that correlation between bell and food and the reward. So the reward is very nicely predicted from the bell, but it's not causal. So if the bell doesn't or rings, it doesn't mean 100% the food will come, and if it doesn't ring, it doesn't mean the food will not come. So that's a deep problem also today about causality and correlation. Or another example, so if you get a stomach virus, and from that you get sick, you get nausea, and it happens that at the time you were eating chocolate, which has nothing to do with getting nausea because it was the virus, then maybe later on the person still gets a nausea reaction, even if just by the smell of the chocolate, because he seemed to have learned in maybe one-shot experiment that chocolate gives him nausea, this person, and not the virus, which the person doesn't know about, really. So learning was also studied in psychology, so habituation. Essentially, it's sort of associative type of learning. Sensitization means if you're exposed to something very often, you maybe lose interest and reaction are less. Sensitization is exactly the opposite. You get a stimulus, and maybe you get more sensitive to the stimulus and have a more severe reaction. Familiarization is the opposite, that you get bored because you always get the same input and you ignore it. Classical conditioning, we just learned about the association of the bell and food, learning to predict. Then there's something called operant conditioning, about the learning of the outcome of behavior, learning to act. Reinforcement learning fits here. Issues are generalization and discrimination learning. So the generalization, can you generalize from what you have learned to interesting new situations? And discriminative learning is when some teacher gives you examples for the class and for the class 1 and class 2, and you're supposed to learn the difference. Social learning is studied, observing other people's behavior and so on. So this is what's going on in psychology. And yeah, one issue here was that these guys were like people like Skinner. I mean, this tradition is great, but they were quite aggressive against people who didn't follow their program and wanted to understand inner working of the brain. So the counter reaction is sort of cognition and cognitive psychology, which attempts to understand the inner working of the black box of the brain. It's a reaction to behaviorism, which only considered input-output. The human behavior is more than stimulus response. And of course, nowadays we have many more ways of measuring brain activities. So we have, it's not just speculative, there's good evidence for certain hypotheses. Introduction of mental processes, it often is algorithmic or computer oriented, what people are doing. We also, it's not just a stimulus, input, output, we are doing reasoning and thinking. And here are some names, William James, a very important American psychologist, Helmholtz, Barkett, George Miller, Noam Chomsky, who studied language, who is also a very opinionated person with a different opinion. So he completely rejected behaviorism, or sort of destroyed it even in some sense. Yeah, cognitive neuroscience is sort of my favorite because it sort of integrates a lot of things. It's about psychology, studying people's behavior. It's about cognition, but it also integrates research in neuroscience, and it really tries to holistically understand what's going on in the brain from very different methodologies. So here's, for example, something which you find in these type of books. So it's an organization of human memory, short-term memory, working memory, long-term memory. Long-term memory is then distinguished between declarative memories, which are things you can talk about, like semantic memory. It's what things you know. Episodic memory is things you remember, like episodes you remember. And non-declarative memories are, for example, perceptual memories, when you improve your vision, or procedural memory, when you improve how to act, playing tennis and so on. Then there's short-term memory, or working memory, which is really your intelligence, or your central executive, so you're the boss in your brain. It's more in the frontal part of your brain. Here's a small illustration about some of these things. So you see something, and perception tells you there's something which looks maybe threatening. And episodic memory helps you to know what to do, because maybe you have a specific memory of an interaction with this object. But maybe you don't need to have an interaction, because you just simply know that lions are dangerous. So you don't have to get personal experience. So this is the knowing, this is the episode, the memorization. These things are declarative, which is quite interesting and important, that we can all verbally report about these experiences. Then we have working memory to know what to do, predict what will happen, decision making and planning. And then we have to act. So we have our brain to act better, not to think better. And acting can be very fast, directly triggered by perception, or by memory, or by thinking. Yeah, so there were also influences of psychology and cognition on machine learning. So the statistical approach in psychology greatly influenced machine learning. So they provided a lot of mathematical tools, which then became part of machine learning. And a neural network, in a sense, is a predictive model, at least some of them. Cognition, so this is psychology. Cognition Maybe we can relate some of the neural networks to cognition and to the inner working of the brain. And there are some people who are studying if deep learning has something to do with the way the brain analyzes images. And machine learning motivates much research in cognition, so it's also going the other way around. And some of the founding fathers of the modern machine learning areas, David Rumelhart and Jeffrey Hinton, are cognitive psychologists. And Hinton, of course, is the founder of deep learning and many other things. So the third one is cellular neuroscience in the non-technical part. So here we are interested in the elementary mechanisms. How does learning really work on the neural and subneural basis? So the hypothesis there must be a physiological change if something is learned or memorized. No? So your brain must change in some way. At least that's the current hypothesis. And the central mechanism is that so-called synapses change their efficiency. It's also called synaptic plasticity, and there's a distinction between short-term plasticity if memory is very short, milliseconds to minutes, and long-term plasticity if the change is hours to lifelong. So, for example, semantic memory would be lifelong. And the central object of interest, of course, is the neuron. So the model is an integrate and fire neuron, so it stays. If nothing happens, there's no inputs. It stays at a negative 70 millivolts. And if the neuron is activated, it depolarizes, so it goes to zero, in the direction of zero. And if it's larger than minus 50 millivolts, it starts to fire. And firing means, so first of all, you see here, so the inputs are these dendrites, so these branches on top. These are the inputs. And if you get enough input, the cell body here fires, and then the action potential travels along the axon, so the output. So the dendrites, they cannot transport information very far, but the axons can propagate like up to a meter. And then you have terminal buttons, which then connect to the dendrites of the next neuron. And so if the neuron is activated, it fires action potentials. So you see them here on the right side. These maybe 2 millisecond distance, and then at some point they stop firing. So it's considered a leaky integrator. So it sort of integrates the inputs from the dendrites, but then also forgets about them. So if the neuron doesn't continue to get excited, it will stop firing. And in some way, the output, so this firing rate, so how often it fires per unit time, it's considered the activation of the neuron. And the critical thing for learning is the synapse, so the connection between an axon and a dendrite. So axon is from presynaptic neuron. They're different, in between the axon and dendrite are the neurotransmitters. So the axon releases the neurotransmitters, and they activate or caught up by the receptors on the dendritic side, and this results in a potential change. And this mechanism is quite complex, and there are many different neurotransmitters, and currently we typically more or less ignore this. But there's a lot of detail we don't include in our mathematical models, obviously. So this is the aplysia, the sea snail I was mentioning before, and Richard Kendall got the Nobel Prize for, or Eric Kendall, for studying this beast. Got the Nobel Prize in 2000, and he was studying the gill with withdrawal reflex. So if you touch the gill, it sort of retracts. It involves 24 sensory neurons and 6 motor neurons, and he could demonstrate habituation, so the reduction of neurotransmitters with repeated stimulus, and also the opposite, sensitization, increase of neurotransmitters with repeated maybe damaging or threatening to damage stimulus, and also association that the electric shock makes the gill retract, but if you touch it with the light, then at some point the light will also do it. So like in the Pavlov dog. And he also studied all these mechanisms in great detail involving the cell nucleus and so on. I left this slide away. But what he found is also new evidence for Hebb's law, which is a very important learning rule discovered very early by Hebb. So when when an axon of cell A is near enough to excite cell B, and repeatedly or persistently takes part in firing it, so it doesn't have to be the only cell which activates it, but it must be part of it, then some growth process or metabolic change takes place in one or both cells such that A's efficiency as one of the cells firing B is increased. So this is a complicated sentence. Sometimes it's shortened to neurons that fire together, wire together. So it means that the axon, so let's say the signal coming into the neuron, has to be active, and at the same time the cell body of the postsynaptic cell must be active. So if both are active at the same time, then synapse sort of becomes stronger. And that's called Hebb's law. If they're not firing together, they seem to decrease their efficiency. So that's not so well known, but also nicely phrased. And neurons out of sync lose their link. And this is confirmed biologically by Kendall, but also with studies in the hippocampus, which is a system for memory formation. So this rule is very simple, and it doesn't talk about synapses and any detail. So that's also always an important question: how much biological details is important to cover the gist of the effect or the most important mechanisms. And for example, for why spiking of the neurons was modeled, and people thought this is extremely important. Now it's lost a little bit its attractiveness. People ignore it more or less. So these are the important paradigm shifts we are talking about. They're not. But this is already changing a little bit. So cellular neuroscience and neurocircuitry are currently not a major focus in machine learning, but are areas of interest, and there's, I think, increasing activity again. But machine learning tries to maintain some of the properties of biological learning. So, for example, learning should be, or the whole functioning should be distributed, so it should not have a CPU type of thing. And that's why we have neurons in our deep neural networks. Also gives you robustness, for example, and fault tolerance. This multi-layered hierarchical computing you find in current neural networks. There's something called convolutional architectures we will learn about, which sort of mimics early processing in the visual processing of visual inputs, fault tolerance and noise resistance, so you can lose quite a number of your brain cells and recover. So there seems to be some sorts of redundancy in the system. But this is an ongoing debate, and it's also, this is one of these paradigm things. So sometimes people see a stronger connection, sometimes they don't see a very strong connection. So it's backpropagation, the learning rule we are using, biological plausible, which is often discussed, is a deep neural network architecture, biological plausible. So typically, people don't claim that neurons are neurons, but the operations neurons in a machine learning system are doing might be, for example, equivalent to a set of neurons in the biological world.